Okay, Mr. G here. Now it's time for us to practice the solutions for the problems that you attempted doing average atomic mass. If you didn't do so hot the first time, like always, it's okay. These are the first problems you attempted, so let's go over them together to see the process that I use to work them out so that you can come up with a process yourself. One of the things you're going to learn in chemistry very quickly that it's important to develop a problem-solving strategy for your problems. That means that when you attempt a problem or you come up with a problem that you find challenging, you've already come up with a strategy that allows you to focus and give you a plan so that you don't panic. And so I'm going to show you the problems that, or rather the strategies that I have developed for this type of problem. The first problem wants us to solve the average atomic mass for the element hydrogen. And it gives us a chart with the stable isotopes, their percent abundance on Earth, and their associated atomic masses. So the way that I attempt to strategize these problems is I first write the isotopes, one on top of the other. And this sets me up to make two rows. Next, I'll write either the percent abundance, oops, that's a 9, 8, 5, or the atomic mass next. It doesn't matter which one you do next. Those are the percent abundances for those isotopes. And then in the next column, you'll see I'm forming sort of a data table as it was shown to you. The atomic masses in AMUs. Now, remember that the type of average we're taking here is not a straight average. It's a weighted average because each isotope has a different abundance. So we need to take the fraction of each isotope's mass and then add them up to get our final answer. And because the abundance is expressed in a percent out of 100, we need to get that in its decimal form to be able to obtain our fraction by multiplication. Out of 100 means that this number is divided by 100. So let's take it out of that form and move the decimal point over 2 places. That'll get us the number we need so that when we multiply the mass by that fraction, or by that abundance, we're actually getting the fraction that it represents. And so that's the next step, is to multiply the abundance by the mass, and we'll get the fraction that mass actually represents. So we'll get our 4-function calculator out. We're going to multiply 0.99985 by 1.0078, and that's going to give us 1.0076483. Now we multiply 0.00015 by 2.0140. That's going to give us 0.0003021. Now, using my strategy here, I've set myself up for success because the next step is going to be addition. And whenever I do addition in this class, I want to do it vertically because of sig figs. Now, you'll notice that I haven't marked my sig fig, so I need to do that. This number has 5. This number has 2. This number has 5. And this number has 5. Which means when I multiply these two numbers, this number should have 5. 1, 2, 3, 4, 5. So we'll stop at the 6. And multiplying 2 sig figs by 5, that number should have 2 sig figs. So we'll stop at the 0. Now I know where to draw my vertical line, just to the right of the 6. And that's really important to tell us where we're going to be rounding in our final answer. So let's do our addition. We can just whip out our 4-function calculator. 1.0076483 plus 0.00003021 gives us 1.0079509 and a 3. Now we know where to round, right at our 9. We look to the right, ooh, we see a 5. We stop. Are there any non-zero numbers to the right of the 5? Yes, there are. There's 9 and 3. So that means we're going to round our 9 up. 9 rounds up to a 10, carries that 1 over to the 7, which makes it an 8, which means our final answer in atomic mass units will be 1.0080 AMUs. So now we have a strategy down. Let's go ahead and practice again on our second practice problem. Okay, for our second problem, we want to find the average atomic mass of carbon, given its 2 stable isotopes. So we're going to follow the same strategy. We're going to list our 2 isotopes, carbon-12, carbon-13. We're going to write our percent abundances. And then our masses for each isotope, that is 4 zeros, in AMUs. We're going to move our decimals over 2 places. And folks, just to be frank with you, this is the one thing that I see people mess up on the most, is in numbers like this, they don't move their decimal over enough places. They might only move it over 1 instead of 2 decimal places. And so that throws off the entire calculation. Then we're going to multiply. I'll go ahead and do my sig figs now. 4, 3, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, we're going to multiply the 0.9889 by 12.0000. Well, let's get my calculator out here. Get 11.8668. Multiply 0.0111 by 13.0034 and get 0.14437774. Set myself up for addition. I'm going to have 4 sig figs in this number, and 3 in this number. Tells me where to draw my vertical line, so I know where to round. 4-function calculator, let's add 11.8668 plus 0.14437774. That gives me 12.0 0.0113774. All right, so rounding here, I look to the right, stay the same. Final answer, 12.01 AMU. Now the nice thing is you can check yourself on these actual elements by looking at the periodic table. If we take our periodic table and we look at this, we can see that it matches. Now the significant digits are different because the individuals who calculated the actual average atomic masses on our periodic tables had much more precise and accurate equipment for calculating the abundances. So their sig figs are more. I think it's 12.0114 maybe on your periodic table. So sig figs will be a little different, but you know your answer is right if it matches, the first couple of sig figs, right? So there you go. That's how you do it. Let's do our last practice problem. Okay, so here's a problem more like that you might see on a test where it's some made-up element. That way you can't just grab your answer off the periodic table, right? You actually have to show that you know what you're doing. So here we have an element on Venus that you discovered, which this could be completely legitimate if someday we were to go there. Conditions are so extreme, perhaps isotopes could be more stable in certain places there. So we are told that our isotopes are VE, we'll say, 301, 302, and 303, right? Next it gives our abundances, and let's just write them already as decimals, right? If it's 92.44, then it's 0.9244. And if it's 6.55%, then it's 0.0655, right? Because we're moving our decimal over 2 places. The last percent abundance was 1.01%, so it's 0.0101. We're going to multiply those by their AMUs. VE301 was 300.876 AMUs. 302 was 301.998. And 303 was 302.998 AMUs. Let's mark our sig figs. 4, 3, 3, 6, 6, and another 6 equals. And so when we have our strategy down, we can do these problems fairly fast. I know I've had a lot of practice though. Alright, so we'll multiply our first isotope and get its fraction. 0.29244 times 300.876. That gives me 278.1297744. Next one, 0.0655 times 301.998. That gives me 19. Ooh. I need to move that over. My decimals need to line up. 19.780869. And lastly, 0.011 times 302.998. That gives me 3 0.0602798. Let's mark where our sig figs go. We're going to have 4 here. 1, 2, 3, 4. 3 here. 1, 2, 3. 3 here. 1, 2, 3. Vertical line's going to go right down here. Let's add that up with our calculator. 278.12977.4 plus 19.7808869 plus 3.060277. Oop, back button. 98. Enter. Here we go. We got 300.9. I'm just going to stop there because I know it's going to round up, right? 9's going to round up because of my 7. So that's going to give me 3, 0. 9 goes up to 10, 1.0 AMUs. And there we have it. Vanadium has an average atomic mass on Venus, not other places in the universe, not on Earth, if we even found it on Earth, of 301.0 AMUs. So there you have it, folks. Practice makes perfect. Trust me, you'll get some practice. And we're going to do some more advanced problems with these next.